Chapter 4, Part 2 of Airplane Flying Handbook, Volume 1. This is a Librivox recording. All Librivox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 4, Part 2. Approaches to stalls. Imminent stalls. Power on or power off. An imminent stall is one in which an airplane is approaching a stall but is not allowed to completely stall. This stall maneuver is primarily for practice in retaining or regaining full control of the airplane immediately upon recognizing that it is almost in a stall, or that a stall is likely to occur if timely preventative action is not taken. The practice of stalls is of particular value in developing a pilot's sense of feel for executing maneuvers in which maximum airplane performance is required. These maneuvers require flight with the airplane approaching a stall and recovery initiated before a stall occurs. As in all maneuvers that involve significant changes in altitude or direction, the pilot must ensure that the area is clear of other air traffic before executing the maneuver. These stalls may be entered and performed in attitudes and with the same configuration of the basic full stalls or other maneuvers described in this chapter. However, instead of allowing a complete stall when first buffeting or decay of control effectiveness is noted, the angle of attack must be reduced immediately by releasing the back elevator pressure and applying whatever additional power is necessary. Since the airplane will not be completely stalled, the pitch attitude needs to be decreased only to a point where minimum controllable airspeed is attained, or until adequate control effectiveness is regained. The pilot must promptly recognize the indication of a stall and take timely, positive control action to prevent a full stall. Performance is unsatisfactory if a full stall occurs, if an excessively low pitch attitude is attained, or if the pilot fails to take timely action to avoid excessive airspeed, excessive loss of altitude, or a spin. Full stalls power off. The practice of power off stalls is usually performed with normal landing approach conditions, in simulation of an accidental stall occurring during landing approaches. Airplanes equipped with flaps and/or retractable landing gear should be in the landing configuration. Airspeed in excess of the normal approach speed should not be carried into a stall entry, since it could result in an abnormally nose-high attitude. Before executing these practice stalls, the pilot must be sure the area is clear of other air traffic. After extending the landing gear, applying carburetor heat if applicable, and retarding the throttle to idle, or normal approach power, the airplane should be held at constant altitude in level flight until the airspeed decelerates to that of a normal approach. The airplane should then be smoothly nosed down into normal approach attitude to maintain that airspeed. Wing flaps should be extended and pitch attitude adjusted to maintain the airspeed. When the approach attitude and airspeed have stabilized, the airplane's nose should be smoothly raised to an attitude that will induce a stall. Directional control should be maintained with the rudder, the wings held level by the use of the ailerons, and a constant pitch attitude maintained with the elevator until the stall occurs. The stall will be recognized by clues, such as full-up elevator, high descent rate, uncontrollable nose-down pitching, and possible buffeting. Recovering from the stall should be accomplished by reducing the angle of attack, releasing back elevator pressure, and advancing the throttle to maximum allowable power. Right rudder pressure is necessary to overcome the engine torque effects as power is advanced and the nose is being lowered. Figure 4-5. The nose should be lowered as necessary to regain flying speed and returned to straight and level flight attitude. After establishing a positive rate of climb, the flaps and landing gear are retracted as necessary, and when in level flight, the throttle should be returned to cruise power setting. After recovery is complete, a climb or go-around procedure should be initiated, as the situation dictates, to assure a minimum loss of altitude. Recovery from power-off stalls should also be practiced from shallow banked turns to simulate an inadvertent stall during a turn from base leg to final approach. During the practice of these stalls, care should be taken that the turn continues at a uniform rate until the complete stall occurs. If the power-off turn is not properly coordinated while approaching the stall, wallowing may result when the stall occurs. If the airplane is in a slip, the outer wing may stall first and whip downward abruptly. This does not affect the recovery procedure in any way. The angle of attack must be reduced, the heading maintained, and the wings leveled by coordinated use of the controls. In the practice of turning stalls, no attempt should be made to stall the airplane on a predetermined heading. However, to simulate a turn from base to final approach, the stall normally should be made to occur within a heading change of approximately 90 degrees. After the stall occurs, the recovery should be made straight ahead with minimum loss of altitude and accomplished in accordance with the recovery procedure discussed earlier. Recoveries from power-off stalls should be accomplished both with and without the addition of power, and may be initiated either just after the stall occurs or after the nose has pitched down through the level flight attitude. Full stalls power on. Power on stall recoveries are practiced from straight climbs and climbing turns with 15 to 20 degree banks to simulate an accidental stall occurring during takeoffs and climbs. Airplanes equipped with flaps and/or retractable gear should normally be in the takeoff configuration. However, power-on stalls should also be practiced with the aircraft in a clean configuration, flaps and/or gear retracted, as in departure and normal climbs. After establishing the takeoff or climb configuration, the airplane should be slowed to the normal liftoff speed while clearing the area for other air traffic. When the desired speed is attained, the power should be set at takeoff power for the takeoff stall or the recommended climb power for the departure stall while establishing a climb attitude. The purpose of reducing the airspeed to liftoff airspeed before the throttle is advanced to the recommended setting is to avoid an excessively steep nose-up attitude for a long period before the airplane stalls. After the climb attitude is established, the nose is then brought smoothly upward to an attitude obviously impossible for the airplane to maintain, and is held at that attitude until the full stall occurs. In most airplanes, after attaining the stalling attitude, the elevator control must be moved progressively further back as the airspeed decreases until, at the full stall, it will have reached its limit and cannot be moved back any farther. Recovery from the stall should be accomplished by immediately reducing the angle of attack, by positively releasing back elevator pressure, and, in the case of a departure stall, smoothly advancing the throttle to maximum allowable power. In this case, since the throttle is already at the climb power setting, the addition of power will be relatively slight. Figure 4-6. The nose should be lowered as necessary to regain flying speed with a minimum loss of altitude and then raised to climb attitude. Then the airplane should be returned to the normal straight and level flight attitude, and when in normal level flight, the throttle should be returned to cruise power setting. The pilot must recognize instantly when the stall has occurred and take prompt action to prevent a prolonged stall condition. Secondary stall. This stall is called a secondary stall since it may occur after a recovery from a preceding stall. It is caused by attempting to hasten the completion of a stall recovery before the airplane has regained sufficient flying speed. Figure 4-7. When this stall occurs, the back elevator pressure should be released just as in normal stall recovery. When sufficient airspeed has been regained, the airplane can then be returned to straight and level flight. This stall usually occurs when the pilot uses abrupt control input to return to straight and level flight after a stall or spin recovery. It also occurs when the pilot fails to reduce the angle of attack sufficiently during a stall recovery by not lowering pitch attitude sufficiently, or by attempting to break the stall by using power only. Accelerated stalls. Though the stalls just discussed normally occur at a specific airspeed, the pilot must thoroughly understand that all stalls result solely from attempts to fly at excessively high angles of attack. During flight, the angle of attack of an airplane wing is determined by a number of factors, the most important of which are the airspeed, gross weight of the airplane, and the load factors imposed by maneuvering. At the same gross weight, airplane configuration, and power setting, a given airplane will consistently stall at the same indicated airspeed if no acceleration is involved. The airplane will, however, stall at a higher indicated airspeed when excessive maneuvering loads are imposed by steep turns, pull-ups, or other abrupt changes in its flight path. Stalls entered from such flight situations are called accelerated maneuver stalls, a term which has no reference to the airspeeds involved. Stalls which result from abrupt maneuvers tend to be more rapid or severe than the unaccelerated stalls, and because they occur at higher than normal airspeeds and/or may occur at lower than anticipated pitch attitudes, they may be unexpected by an inexperienced pilot. Failure to take immediate steps toward recovery when an accelerated stall occurs may result in a complete loss of flight control, notably power-on spins. This stall should never be practiced with wing flaps in the extended position due to the lower G-load limitations in that configuration. Accelerated maneuver stalls should not be performed in any airplane which is prohibited from such maneuvers by its type certification restrictions or Airplane Flight Manual, AFM, and/or Pilot's Operating Handbook, POH. If they are permitted, they should be performed with a bank of approximately 45 degrees, and in no case at a speed greater than the airplane manufacturer's recommended airspeeds or the design maneuvering speed specified for the airplane. The design maneuvering speed is the maximum speed at which the airplane can be stalled, or full available aerodynamic control will not exceed the airplane's limit load factor. At or below this speed, the airplane will usually stall before the limit load factor can be exceeded. These speeds must not be exceeded because of the extremely high structural loads that are imposed on the airplane, especially if there is turbulence. In most cases, these stalls should be performed at no more than 1.2 times the normal stall speed. The objective of demonstrating accelerated stalls is not to develop competency in setting up the stall, but rather to learn how they may occur and to develop the ability to recognize such stalls immediately and to take prompt, effective recovery action. It is important that recoveries are made at the first indication of a stall, or immediately after the stall has fully developed. A prolonged stall condition should never be allowed. An airplane will stall during a coordinated steep turn exactly as it does from straight flight, except that the pitching and rolling actions tend to be more sudden. If the airplane is slipping toward the inside of the turn at the time the stall occurs, it tends to roll rapidly toward the outside of the turn as the nose pitches down, because the outside wing stalls before the inside wing. If the airplane is skidding toward the outside of the turn, it will have a tendency to roll to the inside of the turn because the inside wing stalls first. If the coordination of the turn at the time of the stall is accurate, the airplane's nose will pitch away from the pilot just as it does in a straight flight stall, since both wings stall simultaneously. An accelerated stall demonstration is entered by establishing the desired flight attitude, then smoothly, firmly, and progressively increasing the angle of attack until a stall occurs. Because of the rapidly changing flight attitude, sudden stall entry, and possible loss of altitude, it is extremely vital that the area be clear of other aircraft and the entry altitude be adequate for safe recovery. This demonstration stall, as in all stalls, is accomplished by exerting excessive back elevator pressure. Most frequently, it would occur during improperly executed steep turns, stall and spin recoveries, and pullouts from steep dives. The objectives are to determine the stall characteristics of the airplane and develop the ability to instinctively recover at the onset of a stall at other than normal stall speed or flight attitudes. An accelerated stall, although usually demonstrated in steep turns, may actually be encountered anytime excessive back elevator pressure is applied and or the angle of attack is increased too rapidly. From straight and level flight at maneuvering speed or less, the airplane should be rolled into a steep level flight turn and back elevator pressure gradually applied. After the turn and bank are established, back elevator pressure should be smoothly and steadily increased. The resulting apparent centrifugal force will push the pilot's body down in the seat, increasing the wing loading and decrease the airspeed. After the airspeed reaches the design maneuvering speed, or within 20 knots above the unaccelerated stall speed, back elevator pressure should be firmly increased until a definite stall occurs. These speed restrictions must be observed to prevent exceeding the load limit of the airplane. When the airplane stalls, recovery should be made promptly by releasing sufficient back elevator pressure and increasing power to reduce the angle of attack. If an uncoordinated turn is made, one wing may tend to drop suddenly, causing the airplane to roll in that direction. If this occurs, the excessive back elevator pressure must be released, power added, and the airplane returned to straight and level flight with coordinated control pressure. The pilot should recognize when the stall is imminent and take prompt action to prevent a completely stalled condition. It is imperative that a prolonged stall, excessive airspeed, excessive loss of altitude, or spin be avoided. Cross-control stall. The objective of a cross-control stall demonstration maneuver is to show the effect of improper control technique and to emphasize the importance of using coordinated control pressures whenever making turns. This type of stall occurs with the controls crossed, aileron pressure applied in one direction and rudder pressure applied in the opposite direction. In addition, when excessive back elevator pressure is applied, a cross-control stall may result. This is a stall that is most apt to occur during a poorly planned and executed base-to-final approach turn, and often is the result of overshooting the center line of the runway during that turn. Normally, the proper action to correct for overshooting the runway is to increase the rate of turn by using coordinated aileron and rudder. At the relatively low altitude of a base-to-final approach turn, improperly trained pilots may be apprehensive of steepening the bank to increase the rate of turn, and, rather than steepening the bank, they hold the bank constant and attempt to increase the rate of turn by adding more rudder pressure in an effort to align it with the runway. The addition of inside rudder pressure will cause the speed of the outer wing to increase, therefore creating greater lift on that wing. To keep that wing from rising and to maintain a constant angle of bank, opposite aileron pressure needs to be applied. The added inside rudder pressure will also cause the nose to lower in relation to the horizon. Consequently, additional back elevator pressure would be required to maintain a constant pitch attitude. The resulting condition is a turn with the rudder applied in one direction, aileron in the opposite direction, and excessive back elevator pressure, a pronounced cross-control condition. Since the airplane is in a skidding turn during the cross-control condition, the wing on the outside of the turn speeds up and produces more lift than the inside wing. Thus, the airplane starts to increase its bank. The down aileron on the inside of the turn helps drag that wing back, slowing it up and decreasing its lift, which requires more aileron application. This further causes the airplane to roll. The roll may be so fast that it is possible the bank will be vertical or past vertical before it can be stopped. For the demonstration of the maneuver, it is important that it be entered at a safe altitude because of the possible extreme nose-down attitude and loss of altitude that may result. Before demonstrating this stall, the pilot should clear the area for other air traffic while slowly retarding the throttle. Then the landing gear, if retractable gear, should be lowered and the throttle closed and the altitude maintained until the airspeed approaches the normal glide speed. Because of the possibility of exceeding the airplane's limitations, flaps should not be extended. While the gliding altitude and airspeed are being established, the airplane should be retrimmed. When the glide is stabilized, the airplane should be rolled into a medium banked turn to simulate a final approach turn that would overshoot the center line of the runway. During the turn, excessive rudder pressure should be applied in the direction of the turn, but the bank held constant by applying opposite aileron pressure. At the same time, increased back elevator pressure is required to keep the nose from lowering. All of these control pressures should be increased until the airplane stalls. When the stall occurs, recovery is made by releasing the control pressures and increasing power as necessary to recover. In a cross-control stall, the airplane often stalls with little warning. The nose may pitch down, the inside wing may suddenly drop, and the airplane may continue to roll to an inverted position. This is usually the beginning of a spin. It is obvious that close to the ground is no place to allow this to happen. Recovery must be made before the airplane enters an abnormal attitude, vertical spiral or spin. It is a simple matter to return to straight and level flight by coordinated use of the controls. The pilot must be able to recognize when this stall is imminent and must take immediate action to prevent a completely stalled condition. It is imperative that this type of stall not occur during an actual approach to a landing, since recovery may be impossible prior to ground contact due to the low altitude. The flight instructor should be aware that during traffic pattern operations, any conditions that result in overshooting the turn from base leg to final approach dramatically increases the possibility of an unintentional accelerated stall while the airplane is in a cross-control condition. Elevator trim stall. The elevator trim stall maneuver shows what can happen when full power is applied for a go-around and positive control of the airplane is not maintained. Figure 4-8. Such a situation may occur during a go-around procedure from a normal landing approach or a simulated forced landing approach, or immediately after takeoff. The objective of the demonstration is to show the importance of making smooth power applications, overcoming strong trim forces, and maintaining positive control of the airplane to hold safe flight attitudes, and using proper and timely trim techniques. At a safe altitude, and after ensuring the area is clear of other aircraft, the pilot should slowly retard the throttle and extend the landing gear, if retractable gear. 1/2 to full flaps should be lowered, the throttle closed, and altitude maintained until the airspeed approaches the normal glide speed. When the normal glide is established, the airplane should be trimmed for the glide, just as would be done during a landing approach, nose-up trim. During the simulated final approach glide, the throttle is then advanced smoothly to maximum allowable power, as would be done in a go-around procedure. The combined forces of thrust, torque, and back elevator trim will tend to make the nose rise sharply and turn to the left. When the throttle is fully advanced and the pitch attitude increases above the normal climbing attitude, and it is apparent that a stall is approaching, adequate forward pressure must be applied to return the airplane to the normal climbing attitude. While holding the airplane in this attitude, the trim should then be adjusted to relieve the heavy control pressures and the normal go-around and level-off procedures completed. The pilot should recognize when a stall is approaching and take prompt action to prevent a completely stalled condition. It is imperative that a stall not occur during an actual go-around from a landing approach. Common errors in the performance of intentional stalls are failure to adequately clear the area, inability to recognize an approaching stall condition through feel for the airplane, premature recovery, over-reliance on the airspeed indicator while excluding other cues, inadequate scanning resulting from an unintentional wing-low condition during entry, excessive back elevator pressure resulting in an exaggerated nose-up attitude during entry, inadequate rudder control, inadvertent secondary stall during recovery, failure to maintain a constant bank angle during turning stalls, excessive forward elevator pressure during recovery resulting in negative load on the wings, excessive airspeed buildup during recovery, failure to take timely action to prevent a full stall during the conduct of imminent stalls. End of Part 2 of Chapter 4.